Hello everyone, I'm Bianca Pascariu, a PhD student in Operational Research at Roma University in Italy, and today I'm going to talk about train routing selection problem for the real-time traffic management. In particular, I'm going to show how we improve the model and the solution of this problem. A brief outline of the presentation. I will first introduce the context, and I will describe how we model the train routing selection problem, briefly called TRSP. Here we propose new cost estimation models, and in the solution method, we will see the proposed parallel and colony optimization and true local search. We then test the benefits of our contributions by computational experiments to conclude with some final remarks and future goals. Let me briefly introduce the main context, which is the real-time relay traffic management problem, briefly called rtRTMP. During real-time operations, unexpected events may cause train delays. Maybe train doors don't close at the station. These are called primary delays. A primary delay usually leads to an infrastructure utilization overlap by two trains if they follow the original schedule. But this is not allowed. So in this case, the signaling system will stop the following train, which will suffer another delay called secondary delay. So solving the rtRTMP translates into providing an optimized rescheduling that minimizes the total secondary delays. And it typically consists in retiming, reordering, and rerouting trains. The rtRTMP is an MP-hard problem whose complexity is highly affected by the size of the instances. So limiting the number of rerouting variables is a strong action to reduce its search space, and so its complexity. So we get to our problem, the train routing selection problem, which consists in selecting the best routing alternatives among the available ones for each train in the network. This is done during a pre-processing to the rtRTMP, and the alternative routes are the only ones to be then used in the rtRTMP solution. Let's see now the TRSP model description. Given a railway infrastructure and the corresponding timetable, we will have a given number of trains in a time window, and each train with a set of alternative routes. We represent the TRSP as a multi-partite graph in which for each train we have an independent set of routes. Two vertices in the graph are connected by an edge if they represent coherent routes and belong to different trains. Two routes are coherent when they satisfy the rolling stock constraint from an infrastructure point of view. So in this graph, each n vertex clique identify a feasible combination of train route assignments, and where n is the number of trains in the network, and each vertex and edge in the graph has a cost. So the question is, which feasible combinations of train routes minimize the total clique cost? Based on the seminal paper on the TRSP by Sama et al. In 2016, the computation of costs considers the expected train entrance time in the network and the undisturbed running time. So the vertex cost is the delay due to the longer running time of a route compared to the timetable one, while the edge cost is assessed as the minimum potential secondary delay of two trains using the two routes based on the train ordering decision. We next refer to this cost as base cost. So in this paper, we propose the integration of the base cost with two new building blocks which affect the edge costs. Reutilization considers the rolling stock reutilization constraints, not just for defining edges between coherent pairs of vertices, but also to compute potential delays. And propagation aims to improve the ability of capturing the impact of knock-on delays among all trains in a clique in the cost computation. By boosting the TRSP route choice through better conflict and scheduling cost estimations, we want to identify the best routes to be used by the rtRTMP solver in order to find highest quality solutions. When the new reutilization building block is added, the edge costs account for the temporal coherence of trains that are using the same rolling stock. Let us consider the pair of trains T1 and T3 in the figure with T3 following T1. And the reutilization operation takes place on the infrastructure resource 1. The temporal coherence consists in respecting the minimum time called process time between the arrival of T1 and the departure of T3 necessary to perform the rolling stock reutilization operations. The second temporal coherence condition consists in ensuring that the common resource where the reutilization takes place cannot be occupied by any other train between the arrival of T1 and the departure of T3. We then propose a clique-dependent cost by using propagation building block. This cost is computed after each clique has been found, and this procedure assigns an additional cost to each edge of the clique to estimate the delay propagation caused by all the routes in the clique. So let us consider the cost of the edge linking vertex C1 and C2, which is equal to 4. This potential delay is suffered by train T2. We thus propagate its potential delay to the edges connecting the route C2 with any other route which has common resources with it, which are C3 and C4. So moving on to the solution method, we propose a parallel ant colony optimization, and in general, this is a meta heuristic which simulates the solution in a way that is also used by ant colony to find the best route while foraging for food. The algorithm adopts the concept of pheromone to keep track of solutions quality. So you can split the algorithm in 3 main activities: ant walk, which consists in ants generation and solution construction; Daemon Actions, where a local search improves the ant search process; and Pheromone update, which is the modification of the pheromone trail accumulated by all the ants. The parallelization implementation relies on the multi-threading OpenMP fork join model, according to which parallel regions can be created within a sequential program. And within the parallel region, each thread has its private memory, and the shared memory with access is available to all threads. In ant walk, each ant of the colony is assigned to a thread and independently builds a clique on the construction graph within its private memory. For each ant, the first vertex is randomly selected, while the rest of the clique is built incrementally by adding one vertex at a time, according to the so-called random proportional rule based on the pheromone trail and the heuristic information, which is related to the cost of the vertices and the edges in the construction graph. The cliques found by the ant colony are processed in the Daemon Actions, where local search is applied on the best solution to move to better neighboring ones. Given a clique, the main idea of the local search relies on finding the worst cost vertex and replacing it with better cost vertex taken from the same partition of the graph in such a way that forms a lower cost clique. One parallel local search proposed consists in select within the best clique several worst vertices, so assign each vertex to a thread which replaces it with a better one. And another parallel local search consists in selecting several best cliques and assign each clique to a train, then apply the full local search. At the end of any local search strategy, the best solution is chosen, which is then used in the pheromone update, and here a certain amount of pheromone evaporates first from all the edges of the graph, and then an additional pheromone is deposited on the edges belonging to the best solution of the iteration. Both these actions are performed in parallel. To each thread is allocated a specific memory of the pheromone matrix. Let's see the computational analysis of the proposed TRSP solution approach carried out on the practical test case of Lille station area in France, which is a complex terminal linked with national and international lines. We consider instances corresponding to a 60-minute time windows of perturbed timetables taken during the peak hours for an average of 39 trains per hour with 170 routing alternatives per trains. We implement our TRSP solver as a pre-processing to the rtRTMP solved using Recife-MILP proposed by Pellegrini et al. In 2016. Since the TRSP is designed to be solved in real time, we give to the algorithm a maximum computation time of 30 seconds, while to Recife-MILP 150 seconds. We first studied the correlation between the TRSP and the rtRTMP solution values. So we ran the experiments on 100 instances, and after generating a random rtRTMP solution for each instance, we compute the corresponding clique cost by base, reutilization, and propagation costs. So looking at the results, we can see that the inclusion of the train delay due to rolling stock reutilization brings the TRSP closer to the rtRTMP compared to the base cost. We can see this in the second graph, and we can notice the upward shift of the values. Here, around 40 solutions are correctly assessed compared to 15 in the base cost. The remaining ones are the solutions with the highest objective function value, which are most likely characterized by train delay propagation. So the propagation cost, which is targeted for these cases, records objective values closer to those of the rtRTMP in these cases, and it correctly assesses around 60 rtRTMP solutions. It also has the best Pearson's correlation coefficient. Next, we look at the performances of the ACO-TRSP algorithm with different number of threads. So again, from the results, we can observe that with low number of threads, the algorithm stagnates in local minima since the number of threads increases. Greater improvements in the final objective values can still be obtained. And moreover, the algorithm parallelization improves the so-called diversification actions, which corresponds to initial descending trend in which more rapid improvements of the solution are obtained. Next, we assess the potential of the proposed TRSP improvements on the rtRTMP solution in terms of optimality gap. This computational analysis is performed under timetable disturbances and infrastructure disruptions. For the comparison, we consider the default algorithm of Recife-Milp, which solves the rtRTMP in 180 seconds of computation, given all available routes as input, and as ACO-based, the seminal TRSP rtRTMP approach proposed by Samaitol in 2016, which implements the single thread and colony optimization with the base estimation cost model. So we compare these solutions with those obtained by solving the TRSP with our parallel algorithm, while considering the different cost estimation models. We thus have P-ACO base, P-ACO reutilization, and P-ACO propagation. From the results, we can see that the parallelization introduced in P-ACO base allow for a wider exploration of the TRSP solution space, which corresponds to a remarkably better quality of the rtRTMP solutions. The results obtained by P-ACO reutilization outperform P-ACO base, indicating that the consideration of rolling stock reutilization information is helpful during the train routing selection process, and the highest correlation between the TRSP and the rtRTMP solutions obtained by approximating train delays by P-ACO propagation actually leads to better routes than P-ACO reutilization. In case of disruptions, the ability to provide good initial train routes becomes important to avoid large train delays. So beside the parallelization, the new costs allow for finding significantly better train routes. P-ACO reutilization, for example, halves the average objective values of P-ACO base, while P-ACO propagation brings additional improvements over P-ACO reutilization. From the results, thus, we can conclude that the proposed model improvements lead to better correlation between the TRSP and the rtRTMP solution, which translates into the ability to recommend higher quality train routes to the rtRTMP. Additionally, the proposed colony optimization performs a better exploration of the TRSP solution space, improving its convergence to good quality solution. Future works will address how changes in the rtRTMP objective function should be reflected in the TRSP, and also new TRSP resolution techniques will be designed and compared. Thank you for your attention.